We want to continue looking at acids and bases with our mysteriously titled KW. So really what we want to look at is water. And water is a really unique molecule because if we think about its molecular structure, it has hydrogen atoms and we put them in the front, right? H2O. We've talked about H atoms in the front corresponding to acids. Well, H2O has got the hydrogens in the front. But if we look at the Lewis structure for water, it has lone pairs, right? It has those lone pairs of electrons on them. And that was what we said made the nitrogen atom in like ammonia into a base. So could water be a base? What does water do? And so it ends up that water is that sort of amphoteric substance that we've talked about previously, that water can do both acid and base Brunstad-Lowry chemistry. And so actually, if you have just two water molecules, you can imagine that one of them behaves as, say, the acid, the other one behaves as the base. So you can have an acid and a base for the water molecule, and you can have an exchange of protons, exchange of the H+, where this now has, as a water molecule with an extra H+, our hydronium cations, and then you also are left with hydroxide. And so two water molecules could react in this way. So we know with, just because you can write a chemical reaction doesn't mean it will actually happen. And so this process is called autoionization. So ionization means turning it into water, or ions. So water turning into the ions, which you'll note the positive and the minus. And auto is just self. So water is turning into ions on its own, because basically your reactants are just two water molecules. So the question would be, does this reaction, we can write it out, does it really happen though? And so as we would expect, the equilibrium constant on this is very small. This is in an equilibrium, right? You can write out the reaction. That means it can theoretically happen where this H changes, this H moves between molecules, but it is definitely equilibrium and it is definitely reactant favored. That's good. That means pure water is mostly just pure water. The two water molecules can react, and you do have in pure water some hydroxide and some hydroniums, and they are linked via this expression, the equilibrium constant Kw. So we know this is a form of a Kc equation. The W stands for water. This is an important enough number that it gets its own form or own kind of abbreviation. Kw is the equilibrium constant for the autoionization of water. And at 25 degrees Celsius, so at room temperature, that is 1.0 times 10 to the negative 14th. Again, since the water reactants are pure liquids, they don't show up in the equilibrium constant. It's just the aqueous products. So this is an equilibrium system. There is still some reaction. So what are the concentrations of hydroxide and hydronium ions in pure water?
All right, so we're looking for the concentrations of hydroxide and hydronium in pure water. And so if we want to look at this, these are concentrations of these ions. We want to think about where are these ions coming from in pure water? And they're coming from a chemical reaction, right? So let's write out the formula for that. So we know it's going to be H2O liquid plus H2O liquid. And this is an equilibrium process that goes to OH minus plus H3O plus. And so we know that these concentrations are going to be based on, how much water you have, what the relationships of all these things are, how much of this reaction happens. We know that how much of this reaction happens is going to be governed by equilibrium. So I have my equilibrium constant expression. Kw is equal to the concentration of OH minus times the concentration of H3O plus. And those are equilibrium amounts that are linked via the equilibrium constant. So what we can do to figure this out is we can set up an ice table. So those are liquids. The water reactants are liquids, so they're not going to show up in my equilibrium constant expression, so I don't really care. I have pure water, so I'm just going to say I start with water. So this is going to be 0 and 0. Because I just assumed that I start with no hydroxide and no hydronium, I have to shift in that direction. The coefficient in the reaction is 1, so it becomes plus x. So equilibrium is x and x. So what that tells me is that Kw is equal to x times x. Kw is equal to x squared. So Kw, the value for Kw is 1.0 times 1.0 times 10 to the negative 14 is equal to x squared, giving me that x is the square root of 1.0 times 10 to the negative 14, which is 1.0 times 10 to the negative 7. That tells me that the concentration of hydroxide is equal to 1.0 times 10 to the negative 7 molar, and the concentration of hydronium is equal to 1.0 times 10 to the negative 7 molar. So this is an equilibrium reaction, so we can use our ice tables, use our previous tools. This is very, very, very reactant favored, right? That Kw is a very, very low number. But we can figure it out that the concentrations are 10 to the negative 7 molar. This is good. This is a good thing. Water, pure water, does not have a lot of these ions floating around in it. Very low concentrations of these ions in pure water. Pure water is mostly pure water. So there are hydroniums and hydroxides in a sample. If you make pure water, there are still hydroniums and hydroxides floating around there. This chemistry does happen to an extent, not a big extent, but to an extent. And we can figure out what that extent is using our equilibrium description.
So this equilibrium of hydronium and hydroxide concentrations is always met whenever you have an aqueous system. So in a neutral system where you have pure water, they are equal to each other. So pure water is neutral, but we know that acids and bases cause the creation of either hydroniums or hydroxide ions. And so we can see that these two things are multiplied, these two concentrations are multiplied together to be a constant. So if one concentration goes up, the other one has to go down, right? Their product always has to equal a constant value. So they are inversely related. So with pure water, we would have a neutral solution. And in a neutral solution, the concentrations of these ions are equal to each other. They have to be balanced together. But in an acidic solution or a basic solution, we have an imbalance. And acidic solutions are defined by having extra hydroniums. There are more hydroniums than hydroxides. And in basic, then, we have more hydroxides than hydroniums. So there's this inherent balance between these two types of ions in every single aqueous solution that is governed by this top reaction, by that reaction equilibrium. And so it's just a question of when you start to imbalance it caused by adding an acid or a base to your solution. So with that in mind, we want to then be able to know what happens when we add base to our liquid, to an aqueous solution. So what's the hydronium concentration in a 0.1 molar solution of NaOH?
So what is the hydronium concentration in a 0.1 molar solution of NaOH? Because NaOH is an ionic compound, it really, NaOH, when it dissolves in a solution, is really sodium cations and hydroxide anions. And so what we want, though, is hydronium concentration. So one thing we want to remember is what exactly is hydronium? And so we can kind of remember hydro means water, but it's nium, so it's an ion, cation. So this is the cation of water. So what I really want is that square brackets H3O plus. And so this is going to be something that comes up a lot when we're dealing with acidic solution or acids and bases in water in aqueous solutions. So we want to be, there's going to be a couple different ways that we can compute this, but what we want to think about, what are the real opportunities we have available to us, what equations, what tools do we have that relate hydronium. And for now, one of our kind of standards is going to be that Kw is equal to the concentration of hydroxide times the concentration of hydronium. And so this right here is what we want. And so the question is, do I have these other values? Well, Kw is a constant, so I always have that, 1.0 times 10 to the negative 14. So the question is, what's the concentration of hydroxide? And so the whole point of this equation is that it relates the concentrations of these two ions. In pure water, they were balanced, but you don't have pure water. You've introduced hydroxide into this solution, which is going to affect this balance between hydroniums and hydroxides. So what we want to do is we want to figure out how has that balance been affected. Well, we know that we started with, we have this 0.1 molar NaOH. Okay? And what that means is that I have 0.1 moles of NaOH per 1 liter. That's just the definition of molarity, moles per liter. But what I really want is the concentration of hydroxide. So in this case, the stoichiometry is just for every 1 mole of the sodium hydroxide that we started with, I produce 1 mole of hydroxide, right? I make 1 mole of sodium, cations, and 1 mole of hydroxide. That was where like the 2 came from when we were doing, say, like boiling point work. So, but it's only, if I only care about hydroxide, it'd be 1 mole of hydroxide dissolved for every 1 mole of sodium hydroxide solid you put in there, giving me 0.1 moles of hydroxide per 1 liter, which is 0.1 molar hydroxide. And so what we can do is we can take this value and plug it in right there. And so our overall equation was Kw is equal to the concentration of hydroxide times the concentration of hydronium. So that's 1.0 times 10 to the negative 14 for Kw is equal to 0.1 for the concentration of hydroxide times the concentration of hydroniums, and I get that the concentration of hydroniums, 1.0 times 10 to the negative 14 divided by 0.1 is equal to 1.0 times 10 to the negative 13 molar. And just like we've seen previously with equilibrium constants, right, this thing is unitless. You just kind of got to know that the concentration of hydronium in the end is going to be in molarity. And basically we can assume that moving forward, just about every concentration will be in molarity. And so one of the things that we can see is that, we know pure water had a balance where these two things were the same. But you add sodium hydroxide, which is a base, right? This is a base that will affect the water, and it has imbalanced the balance of hydroxide and hydroniums. They have a pretty high concentration of hydroxide and a very low concentration of hydroniums.
Another video down. Still looking for questions on participation 224. See you in the next video.